Now we're going to take a break from cryptography to learn a little bit math that is not relevant yet to the cryptography that we're learning, but will be relevant in the future. In particular, we're going to talk about quotients and remainders, something called the quotient-remainder theorem. In another class, you might have seen this called the division algorithm, so if that's something that you're familiar with, that's what we're talking about here. The other thing we're going to look at is a related concept called the mod operator. So we're going to review how we used to do long division with remainders back in the old days. We're going to reinterpret what quotients and remainders meant back then to give us something called the quotient-remainder theorem. Again, you might have seen this as division algorithm. We'll work an example, and then we'll introduce the mod operator and work an example on that one. All right, so remember the good old days when we used to be division, and back when we got freaked out when we couldn't divide evenly when we did a division problem. So when we had 75 divided by 9, we just figured out we had to figure out how to do stuff with remainders. So the way we did that is say, well, how many times can 9 go into 75? What's the most times we can do it? It turns out 8 is the most we can do it without going over 75. We get 9 times 8 is 72, and then we find the remainder by subtracting that from 75, giving us 3. So one way we could say that is when we do 75 divided by 9, that gives us a quotient of 8 and a remainder of 3. Another way we can interpret that is we know that 9 times 8 is 72. We know that 72 plus 3 is our remainder, is equal to 75. And so if we plug in all that information, we get 75 equals 9 times 8 plus 3. That's a nice equation that involves the numbers that we're dividing, the 75 and 9, the quotient 8, the remainder 3, and it gives us the arithmetic about how all those numbers are related. One thing to note about our remainder is that remainder 3 is less than 9, the number we're dividing into. And in fact, no matter what number we divided by 9, in this case it was 75, but it could be any number, we always get a remainder that is most 8. All right, so in general, how is it going to work when we divide one number A by another number B? And these are both integers. So the first thing we're going to do is find the biggest number that when we multiply it by B gives us a number that is not bigger than A, that doesn't go over A. So we're looking for some number Q such that BQ is at most A, and we're looking at the biggest Q that makes that work. Then we just find the remainder by taking that BQ and subtracting it from A. That's our R. And if we want to move things around a little bit, let's say we added BQ to both sides, we would get A equals BQ plus R. And again, we have an equation that has the numbers that we're dividing, A and B, has the quotient Q and the remainder R, and it expresses the relationship between all those numbers. In general, since we're dividing by B, our remainder can be no bigger than B minus 1. In other words, it's always going to be smaller than B. And we always choose remainders so that they're greater than or equal to 0. That's why we choose Q so that BQ is not bigger than A. If BQ were bigger than A, then we get a negative remainder. So our quotient-remainder theorem basically tells us we can always do this and we always get a well-behaved remainder. So in other words, if we have any two integers, A and B, where B is positive, then there exist unique integers Q and R, Q being our quotient, R being our remainder, such that A is equal to BQ plus R, where R is at least 0 and R is no bigger than B minus 1. So in other words, our R is not negative and our R is smaller than B. And the unique means that there's only one possible quotient-remainder pair that you can get. You can't get one Q and R that works and another different Q and R that also work. And another way of saying this theorem is that we can always do long division and end up with a remainder that is smaller than the number we are dividing by. So if we wanted to find the quotient remainder, for instance, when we're dividing 158 by 27, remember we're dividing by 27, so our remainder should be at most 26. Let's see what happens. Well, it's kind of hard figuring out the right quotient. One of the tricky ways of doing it is if we just do the fraction, 158 over 27, just literally do the division and see what hashes out. We'll see that we'll get some number that's between 5 and 6. That means if we try to multiply 27 by 6. That's going to be a number that's too big. That's going to be bigger than 158. So we want to round down to 5. So our biggest integer possible quotient is going to be 5. When we multiply 27 times 5, we get 135. And then we find the remainder by subtracting 135 from 158. That gives us 23 and works out nicely. 23 is less than 27. It's positive, and so it's a perfectly reasonable remainder. And if we want to have our equation that gives us the relationship between the numbers we're dividing, our quotient and our remainder, we get 158 equals 27 times 5 plus 23. So our quotient is 5, our remainder is 23. All right, so now we move on to a concept that's very much related to quotients and remainders, in particular the remainders. We can use quotients and remainders to define something called the mod operator, and the mod operator is where we're really going to be working hard on using that in our cryptography. So suppose we have a and b that are integers, where b is a positive integer. Then we define the number a mod b to be the remainder that you get when you divide b into a. Or another way of looking at that is you do a divided by b. So you're finding a mod b, you do a divided by b, figure out the remainder. That remainder is your a mod b. So if we're trying to compute 500 mod 31, we're still going to have to find the quotient too, even though the quotient by itself isn't important, but we need the quotient to find the remainder. So we're going to use the same trick we did before. We're dividing 31 into 500. We're going to do the literal division, 500 divided by 31. We get a number that's between 16 and 17. That tells us that if we use a quotient of 17, that's going to be too big. And so that 16 is going to be the biggest one possible for us to use. So that means our quotient is 16. If we want to find the remainder, we take 16 times 31. That gives us 496. We subtract 496 from 500 to give us the remainder. And that gives us 4 as our remainder. And our remainder is literally 500 mod 31. So 500 mod 31 is equal to 4. So now that you've seen a little bit of quotient remainder magic and some problems with the mod operator, it's a good time for you to look at the PDF file included with this video. It is called, well, Quotient Remainder and Mod Operator.